We discussed about AC when it is passed through an inductor. There is a phase difference. A current is lagging. That is what we have seen. I equal to 0 sine omega t minus pi by 2 we got. And when AC is passed through a capacitor, what happens? Let us see that. Now, whether there is a lag or lead when AC is passed through a capacitor. That means lag or lead between current and voltage. That is what we have to find out. So here you can see a capacitor. C is the capacitance of the capacitor, and we apply an EMF. We know it is AC. From the symbol you can identify AC is applied across the capacitor. And we know AC current is always varying. Every instant its magnitude is changing and the direction reverses. Periodically it reverses the direction. After half rotation, the direction of current is reversed. So when such a current is passed or connected, when such an EMF, alternating EMF is connected to a capacitor, what happens? That we can study now. So initially we take EMF applied, C equal to E equal to instantaneous value only we are telling. Instantaneous value of EMF E equal to E0 sin omega t. When it is connected to the capacitor, we know it will charge the capacitor. So first half cycle it charges, then next half cycle it will be discharged. This becomes negative, other becomes positive, like that. Charging and discharging will take place when we connect an AC to a capacitor. First half cycle charges, second half cycle it will be discharged, like that. It becomes negative. Then what is the equation for current? Let us see that.
Teacher, can you please admit Devananda?
Okay. Okay. So when capacity, the potential difference developed across the capacitor, this equation we have studied in the chapter, second chapter we have studied V equal to Q by C. So here we have to take the EMF applied. V is equal to E. V equal to Q by C equal to E. That formula you have to take. And E equal to E0 sin omega t. So that is the equation with which we have to start this derivation. EMF applied V equal to Q by C in a capacitor, and that here we take that as E, and E equal to E0 sin omega t. Then next from that we take Q, then dq by dt we find. Then we get the current. Like that we are proceeding. So first we take the equation V equal to Q by C, which is equal to E, that is equal to E0 sin omega t. Then Q you have to find from it. What is our purpose? To find the current, and we have to find out whether there is any phase difference between current and voltage. Devananda not with okay. Okay. So Q equal to, we get C is taken to right side. So Q equal to C E0 sin omega t. If you get Q, how will you get current from it? We know I equal to dq by dt. So differentiating this expression, we get the equation for current. So I equal to d by dt of Q. Substitute for Q. What is Q? C E0 sin omega t. We have substituted. And constants you can take outside. C is the capacitance of the capacitor. It is not varying. And E0 is the peak value of EMF. So that is a constant value, not varying. Peak value will not vary. Instantaneously EMF is varying, but peak value is not varying. Peak value is always a constant. So it is taken outside. C is 0 into d by dt of sin omega t. Differentiation and all you have studied. So you are knowing what is d by dt of sin omega t. It is cos omega t, and again you have to differentiate this function omega t with respect to time. Therefore we get omega, and we have to multiply that with omega. The differentiation, I think you studied that. Okay. So C is 0 cos omega t into omega. Again, we have to differentiate this function. Omega d by dt of omega t. That is omega into dt by dt. dt by dt is 1. So omega is there. With that, you have to multiply this. So C is 0 cos omega t into omega. We got the equation. Remember this equation? I equal to C is 0 cos omega t into omega. The next step we are writing this C omega we are writing in the denominator of this. That is E0 by 1 by C omega. E0 by 1 by C omega we are writing. Then only that will be saved. C omega will come to the numerator. About next step what we are writing E0 by 1 by C omega. Then 1 by C omega is taken as XC. XC is the capacitive reactance. So E0 by XC, that will be I0. Like that we are writing. I0 cos omega t you will get. Next. So next step I told you I equal to E0 by 1 by C omega we are writing. Into sine omega t. See, cos function is changed to sine function. I told you now last class we have to express omega t positive. When we express current equation, omega t must be positive. So here cos function we got. Cos omega t is what we got. That we are expressing in terms of sine in order to find out the phase difference. So expressed in the similar way as voltage is given. So we are expressing current I equal to E0 by 1 by C omega. The cos function is changed to sine function. That is cos omega t. So with the sine, when we express it, we can write either omega t plus pi by 2 or omega t minus pi by 2. Both are possible. Minus pi by 2 equation we have taken for inductor because already there was one minus there. So in order to make it positive, that equation we took. And here we take the plus equation, omega t plus pi by 2. In a capacitor, we take omega t plus pi by 2. Sin omega t plus pi by 2 we take. The current will be maximum, that is I will be equal to the maximum value I0 when this function sin, this takes the maximum value. That is sin of omega t plus pi by 2 is maximum. What is the maximum value of sin? That is what? 1 is the maximum value of sin. So when this factor takes its maximum value, we get the peak value of current. So this is E0 by its resistance. That means position offered by capacitor to AC current. So that we can name as capacitive reactance X suffix C, XC. So the E0 by 1 by C omega into 1. That is the maximum value of current I0. Then substituting that we get this factor becomes I0. So I equal to I0 sin omega t plus pi by 2. So now we can compare both the equation for voltage and equation for current. Equation for voltage E equal to E0 sin omega t. But equation for current, we can see with the omega t, we are adding pi by 2. So this is the phase difference between voltage and current. Pi by 2 is the phase difference between voltage and current. So this is the form of alternating current. Comparing equation 1 and 4, we find that in an AC circuit containing capacitor only, alternating current leads. Plus ചെയ്ത് കഴിഞ്ഞാൽ lead. Minus ആണെങ്കിലോ lags. Inductor current lags. Capacitor current leads by a phase angle of pi by 2. That is what we have seen now. So question will be like that. Show that in a capacitor the current lead, or question will be in another way. That means what is the phase difference between that voltage and current when AC is passed through a circuit containing capacitor alone. So we got the expression for capacitive reactance. Capacitive reactance XC equal to XC, capacitive reactance. It is the opposition offered by capacitor to AC. 1 by C omega. XC equal to 1 by C omega equal to 1 by C into omega equal to 2 pi into nu. All equations you should know. What is XC? 1 by C omega. What is omega? Omega is 2 pi into nu. What is nu? Nu is 1 by T. Okay. And you can see a note here. The inductive reactance limits the current in a purely inductive circuit in the same way as resistance limits the current in a purely resistive circuit. So inductive reactance is the opposition. I told you now it is the opposition offered by inductor to AC. So it also decreases AC current. Inductance. You can use resistor, inductor or capacitor to reduce AC current. So inductive reactance limits the current in a purely inductive circuit in the same way as resistance limits the current in a purely resistive circuit. Clearly, the inductive reactance XL is directly proportional to the inductance, because what is the formula? XL equal to L omega, directly proportional to the inductance. L omega, omega equal to 2 pi into nu. So XL can be written as L omega equal to 2 pi into nu into L. And you know, nu frequency in the case of DC circuit, it is not varying. The frequency is 0. In a DC circuit, frequency is 0. But what is the reactance? If you put 0 here, what is the reactance? XL becomes equal to 0. So DC circuit, you know, inductor offer 0 resistance, 0 reactance to DC current. So inductor is used to reduce AC or DC. I will ask question. Inductor is used to reduce AC or DC. I ask to Vaishak. Vaishak, are you there? Vaishak.
AC.
Yes, correct. Inductor is used to reduce AC current. DC, you know, it is a given easy path because reactance is 0. So 0 resistance it offer. So it gives an easy path to DC, but it offer resistance to AC. And the unit of inductive reactance is ohm, just like resistance unit. Inductive reactance unit is ohm. But L, you know, L unit is Henry. Inductance, Henry. But XL, reactance, unit is same as that of resistance, that is ohm. Then capacitive reactance, X is equal to 1 by C omega. Omega equal to 2 pi into nu. And nu equal to 1 by time period. All these equations you must know. So here, in the case of a DC circuit, let us see what happened. Nu is 0. Nu is 0. DC circuit. In DC circuit, you can it is written there. In DC circuit, nu equal to 0. Frequency not varying. It is a steady current. In DC, nu equal to 0. So XC equal to 1 by 0. 1 by 0, that is infinite. So infinite resistance to DC ആണ് capacitor. It block DC എന്ന് പറയാം. It will block DC. But actually it is not passing, just like a resistor or an inductor, that current is not passing through the capacitor. So it block DC. So when it block DC, but it limit only AC. See, you can see the capacitive reactant decrease limit the amplitude of the current in a purely capacitive circuit in the same way as the resistance limits the current in a purely resistive circuit. Capacitive reactance varies inversely as the frequency of AC. Capacitive reactance vary inversely as the frequency. And XC 1 by 2 pi into nu into C inversely. You can see next page. See, that is the graph for so it block DC but limit AC. That means allow, but its limit decreases. So in order to reduce AC current, which all elements we can use? Reduce AC, we can use resistor, inductor, and capacitor to limit AC current. So but to limit the decrease DC, we use resistor only. The inductor of our DC path, capacitor block DC. Okay. Variation of XL with frequency. Usually 1 mark question this graph asks. We know XL equal to L omega, omega equal to 2 pi nu, 2 pi into nu. They are directly proportional. XL and frequency are directly proportional. Last day I asked a question. Last it was a question. What is the frequency of AC used in our house? You got an answer for that? അക്ഷജിനോടായിരുന്നു ഞാനത് ചോദിച്ചത്. അക്ഷജ്
50 hertz അല്ലേ?
correct answer. Okay, 50 hertz ആണ് കേട്ടോ. 50 cycles per second. In 1 second, 50 such cycles are happening. Okay, 50 cycles per second or 50 hertz. That is the frequency of AC. Okay. So this frequency and reactance, they are directly proportional. Why? XL equal to L omega. Omega equal to 2 pi into nu. So XL is directly proportional to frequency. So we get a graph like this. Frequency along the x-axis, XL, reactance, inductive reactance along y-axis. We get a straight line graph. They are directly proportional. But in a capacitor, X is equal to 1 by C omega. Omega equal to 2 pi into nu. So inversely proportional. Frequency and capacitive reactance are inversely proportional. So we get a graph like this. Inversely. And the graphical representation of AC when it is passed through the capacitor is shown here. That graph is plotted by finding these values. See, omega t is 0. What is the value of EMF? What is the value of current? E equal to 0 sin omega t, but I equal to I0 sin omega t plus pi by 2. Current is leading, so that factor you have to write here. So when omega t is 0, sin 0, 0, E becomes 0. What is I? You see, omega t plus pi by 2. Omega to 0 ആയാലും ബാക്കിയുടെ pi by 2 ഇല്ലേ? Sin 90. Sin takes its maximum value. So I becomes equal to I0. So EMF is 0, but current is maximum. EMF is 0, current is maximum value. Like this. Next value we can find out pi by 2. Omega t pi by 2 sin 90. So E becomes equal to E0. Correct. Then what is I? Omega t is 90 now. Omega t is pi by 2. So pi by 2 plus pi by 2, what is it? Pi വരും 180 വരും അല്ലേ? 90 plus 90 180 വരും. Sin 180 എന്താണ്? 0 ആണ്. So this factor becomes 0. I becomes 0. So EMF takes its maximum value. Current takes its 0 value. EMF takes its maximum value. Pi by 2 angle ആയിപ്പോ. EMF takes its maximum value. But current, minimum value, it becomes 0. So like that, you have to find out all the values of pi, the pi by 2 like that. And you will get the corresponding values for E and I. And when we plot a graph with that, we get a graph like this. So they are not in phase, it shows. They are not in phase. Current is leading the EMF by a phase angle of pi by 2. That is the graph. Next is a AC circuit containing all the elements are there: inductance, resistance, and capacitance. In series, it is a very important derivation. All the three elements are present. So it is asked as a 5-mark question like that. All the three elements are present in the AC circuit. Which are they? LCR, RLC, series circuit. They are connected in series. RLC, R means resistor, L means inductance or inductor connected, and C means capacitance. So capacitor is connected. All the three elements are connected in series. That's important. Series connection is what we have to study here. So that diagram I'll show you. This is the circuit diagram for RLC circuit. RLC circuit. A resistor, inductor, and a capacitor are connected in series. Series connection and it is connected to source of EMF. So connected to an EMF. Actually, situation omega t plus 5/2 is there. 5 plus 5 is there. I will tell you later. So here EMF is connected. Okay. Then the current, as they are connected in series, current through each element is same. Current through each element is same. Why? They are connected in series. Series connection we have studied. Current through each element will be same. And that's why it is marked here. In order to show the phase difference, small diagrams are shown below each component. So resistor, current and voltage are in same phase. VR means voltage across the resistor. When current is passed through the resistor, there will be potential drop across each component. Suppose VR is the potential drop across the resistor. We know when AC is passed through a resistor, current and voltage are in phase. So they are marked like this, in phase, same direction. But inductor, we have seen that current is lagging. So current in all elements we have shown the same direction. And if current is lagging, voltage is leading. So VL you have to write here. VL is leading, current is lagging. That is what we have shown. That means VL is leading by a phase angle of 90. VL is leading. So you have to put an arrow mark like this. ഇങ്ങോട്ടാണ് arrow mark. ആൻറ്റി ക്ലോക്ക് വൈസിലാണ് arrow mark. അതായത് ലീഡ് ചെയ്യുമ്പോൾ ലാഗ് ചെയ്യുമ്പോൾ ക്ലോക്ക് വൈസിൽ ലീഡിങ് എന്ന് കാണിക്കണമെങ്കിൽ ആൻറ്റി ക്ലോക്ക് വൈസിലാണ് നമ്മൾ റൊട്ടേറ്റ് ചെയ്യുക. സോ ഹിയർ ഇറ്റ് ഈസ് VL. And here, yes.
ലീഡ് ചെയ്യുമ്പോൾ ആന്റി ക്ലോക്ക് വൈസിലാണോ?
ഏതാ?
ലീഡ് ചെയ്യുമ്പോൾ
ലീഡ് ചെയ്യുന്ന കാര്യങ്ങൾ, പ്ലസ് ചെയ്യുന്ന കാര്യങ്ങളാണ് നമ്മൾ ആന്റി ക്ലോക്ക് വൈസിൽ. അതെ, ഇവിടെ നോക്കൂ, വോൾട്ടേജ് ഇതാണ് നമ്മൾ എടുത്തിരിക്കുന്നത്. വോൾട്ടേജിനെ സംബന്ധിച്ചിടത്തോളം കണ്ട ഇത് ലാഗ് അല്ലേ, കറണ്ട് ആന്റി ക്ലോക്ക് വൈസ് അല്ലേ. കറണ്ട് വിത്ത് റെസ്പെക്ട് ടു കറണ്ട് വോൾട്ടേജ് ഇസ് ലീഡിങ്. കണ്ടാ ഇങ്ങോട്ട് phase difference 90 degree. They are having a phase difference 90 degree. But we know current is lagging, voltage is leading. And here capacitor, we have seen capacitor, the current is leading. And voltage lag. Voltage lagging, current leading. അപ്പോൾ ഇതാണ് ഫേസ്, നമുക്ക് ഫേസർ ഡയഗ്രത്തിൽ റെപ്രസെൻ്റ് ചെയ്യാൻ ആദ്യമായിട്ട് വരയ്ക്കുന്ന ഡയഗ്രത്തിൽ ഇങ്ങനെ ചെറുതായിട്ട് ഒരു ഇത് മാർക്ക് ചെയ്ത് വയ്ക്കും. അത് കഴിഞ്ഞിട്ട് ശരിക്കുള്ള ഫേസർ ഡയഗ്രാം നമ്മളിവിടെ വരയ്ക്കും. അപ്പോൾ ഇൻ എ റെസിസ്റ്റർ, വോൾട്ടേജ് ആൻഡ് കറണ്ട് ആർ ഇൻ ദ സെയിം ഫേസ്. ആൻഡ് ഇൻ എൻ ഇൻഡക്ടർ, ദാറ്റ് കറണ്ട് ഈസ് ലാഗിങ്. ആൻഡ് ഇൻ എ കപ്പാസിറ്റർ, കറണ്ട് ഈസ് ലീഡിങ്. സെയിം തിങ് ദാറ്റ് വി ഹാവ് സ്റ്റഡീഡ്. And phasor diagram is shown here. This is the phasor diagram. Phasor diagram you see. See here, voltage across the resistor VR represented by VR. That will be current into resistance VR. And then voltage across the inductor VL I0 XL. This is I0 R. This is I0 XL. Suppose this is VL is greater than VC. In such a circuit, if suppose that VL is greater than VC, we have taken that case. VL is greater than VC. So VL we have to represent with a greater vector OB, and the voltage across capacitor is denoted with VC. And according to our assumption, here we have taken VL is greater than VC. So with a smaller length, we represent with VC. VC is represented with a smaller vector. So all the three vectors are represented here. VR, VL we know voltage is leading. Current lagging, voltage is leading. But voltage is lagging. Current is leading. You represent all these in a figure. Phasor, that angle is shown. Phase angle between them is shown clearly. In a resistor, current. This is the current. And voltage are in the same phase. Our direction mark peak value of current, voltage, VR, both are in the same direction, which shows that they are in the same phase. But in an inductor, current is lagging, so voltage is leading by a phase angle 90 degree. That is shown here, VL with the vector OB. VL is represented with the vector OB. VR is represented with the vector OA. And we know capacitor, the voltage is VC. It is represented with the vector OC. Okay, all the vectors are represented here, VR, VL, VC. Then next we have to find out the vector sum of all this. So for making these calculations easy, we are representing all these in a phasor diagram. Now we can find the resultant. See, VL is upwards, acting at this point O, and VC is acting downwards. Its magnitude is less. So, but they are acting in opposite direction. So it is easy to find the resultant of VL and VC. What is the resultant of VL and VC? They are acting at the same point. One is upwards with a greater magnitude, and VC is downward with a smaller magnitude. So the resultant vector will be VL minus VC. And we know VL is greater. So VL minus VC will be upward. For example, I tell this is 0 to B, O to B. That is 5 in magnitude. And this is 2 in magnitude. So what is the resultant of that? 5, vector OB is 5 in magnitude. And vector OC is 2 in magnitude. What is the resultant? 5 minus 2. 5 minus 2. That is the resultant. And it will be in the direction of the greater vector. It will be in the direction of greater vector. So here VL minus VC we have to represent. So resultant of VL and VC we have represented as VL minus VC. So for example 5 minus 2 equal to 3. So with the 3 centimeter length we have to represent OB dash equal to 3. Like that example I told you. So VL minus VC. Now the resultant of VL and VC we got, that is VL minus VC. Now we have only two vectors. One is VL minus VC, other is VR. How will you find the resultant of that? Now we have two vectors, which is one is VL minus VC, which is represented by OB dash, and the other vector is this one, VR. Two vectors are there. Now how will you find the resultant? Using the parallelogram law of vector addition. Complete the parallelogram with VL minus VC as one side and VR as the other side, which are starting from the same point O. Complete the parallelogram with dotted lines and draw the diagonal from the point O. That will give the resultant voltage E0. So resultant voltage E0 is given by or given with the vector OK. It is given with the vector OK, which is equal to square root of OA square plus O. See, what is the formula to find the resultant? using parallelogram law of vector addition, s square plus b square plus 2ab cos theta. That is the formula. Here s square, that means vr square. B square, VL minus VC whole square plus 2AB cos theta. 2AB cos theta is not seen here. Why? Can you tell? S square plus B square plus 2AB cos theta. That is the general formula we have studied. But here 2AB cos theta, that term is not there. Can you tell why? 2AB, suppose A is this and B is this. 2AB cos theta. What is the angle between them? Between these two vectors, angle between these two vectors is 90. So 2AB cos 90 it becomes. Cos 90 0. So third term will not be there because it is 0. 2AB cos 0, that term will not be there. So with this term we can write the equation. Third term becomes 0. 2AB cos 0 cos 2AB cos 90. So that term will not be there. Okay, so we got the expression OK equal to root of YS square plus OB square, root of VR square plus VL minus VC whole square, and VR is voltage across the resistor. How will you get voltage across the resistor? A peak value of current into its resistance. Peak values are taken. I0 R whole square plus VL I0 XC current into resistance, reactance. I0 XC minus I0 XL minus I0 XC, the whole square. I0 is common factor. I0 square here, I0 square is there. Here also I0 square is there. So that is taken outside the square root. So it becomes I0. I0 into root of R square plus XL minus XC whole square. The total effective resistance of the RLC circuit is called the impedance of the circuit. Here this is E0, this is I0. What will be E0 by I0? E by I, according to Ohm's law, peak value of EMF by peak value of current. What will be? I will ask to Amish, what is E0 by I0? Amish, voltage by current, what is it? Amish? No answer, Amish is not there. Gayatri, can you tell E0 by I0? Gayatri? No answer. E0 by I0. Then I'll ask to Abhirami. Abhirami. E0 by I0, what it will be?
R0 resistance.
Resistance. Okay. R only. Okay. So E0, correct answer, E0 by 0 will be the resistance of the circuit. We cannot tell R because that is a new term to you. That is known as impedance of the circuit. So E0 by I0 will give the impedance of the circuit. Impedance means the total opposition offered by all the three elements to the AC circuit. So impedance, what is impedance? Impedance is the total effective opposition offered by all the three elements in the, which are the three elements? Resistor, inductor and capacitor together, all together. They offer some resistance to AC and that is known as impedance of the circuit. 5 minutes more? Oh, one derivation or two derivation. Okay. What happened? Now it's not something happened. Amish is waiting in the lobby. Oh, that's right. Two participants are waiting. Amish and Sivagal. I will stop sharing because something happened. Again share. Oh my God. Next. Again came back. Okay. So we got the equation for impedance. Impedance E0 by I0 is known as impedance of the circuit. That's equal to square root of R square plus XL minus XC all square. From the figure, it is clear that in an AC circuit containing R, L, C, the voltage leads the current by a phase angle phi. Have you seen that? This diagram. See, here this is the resultant voltage, diagonal. Diagonal gives the resultant voltage E0. It is having a phase angle of phi. It is with respect to this current, it is leading. Voltage is leading, anti-clockwise direction we have to rotate. So this is leading by a phase angle of phi. EMF is leading by a phase angle of phi. Understand? So this phi is the phase angle between the current. Current is along this x-axis. We have marked current is along x-axis, and the voltage we got now along this diagonal. Okay. So the relationship between them in an RLC circuit, the voltage is leading the current by a phase angle of phi. You cannot tell pi or pi by 2. It is marked as phi. Phi is the phase angle by which the voltage leads the current. Okay. Then the direction also you have to find out. Tan phi will give this gives the magnitude. E0 we got the equation, then impedance also we have calculated. Total opposition offered by all the three elements to the AC current, that also we have found out. Then direction, magnitude and direction of EMF, both we have to find out. Direction is found by finding the angle tan phi. Tan phi, let us take the figure again. Figure is needed tan phi for finding tan phi. Tan phi, see tan phi opposite side. That is AK, that is VL minus VC, and adjacent side VR. VL minus VC by VR. Okay. Tan phi, VL minus VC by VR. See, VL minus VC by VR. And VL equal to I0 XL and VC equal to I0 XC. So I0 is taken as common factor, I0 into XL minus XC by I0 into R. I0 get cancelled and we get tan phi equal to XL minus XC by R. So we got the magnitude and direction of the EMF